Swayam Prabha. Digital India. Educated India.
At T2, okay, the energy absorbed would be half L I square from 0 to IL, which basically gives you half L IL squared. Okay. Now, this means that an inductor stores an energy of half L IL squared, that is half of inductance times the square of the current through the inductor. And just by similar logic that we employed earlier, okay, we can show that by discharging from some current IL to zero current, you can recover all of the energy. Okay, so the inductor also does not dissipate any energy, and it stores an energy of half LIL square. It also doesn't depend on how you reach IL. You could reach it gradually, you could reach it abruptly, and you could go back and forth between positive and negative values and reach that. Okay, so as long as you are at a current of IL, you will have an energy stored which is half of LIL square in the inductor. Okay, any questions about this? Okay, there is one question. It says basically it asks what is the difference between an inductor and a capacitor. Now, I mean, the I and V relationships are different. Okay, for a capacitor, you have a voltage V across it and a current I through it. I is C times dV by dt. And in an inductor, if you have a voltage across it and a current through it, I is L di by dt. Okay, so as far as circuits, as far as the terminal characteristics are concerned, it's like the roles of current and voltage have reversed. Okay, in a capacitor, the current is the time derivative of voltage, and in an inductor, sorry, I made a mistake here, this should be V, the voltage is the time derivative of current. Okay, so that's all there is there to it. And physically, of course, there is a difference. A capacitor stores energy in the form of electric fields, and an inductor stores energy in the form of magnetic fields. Okay. In other words, another way of saying it is a capacitor stores voltage and an inductor stores flux linkage. Okay. Inductor stores current. Inductor stores a current. Now there is another interesting question, which is that if a capacitor behaves as, if a capacitor can absorb power and also deliver power, is it an active element or a passive element? Okay. So this was the question. Okay. Now again, I would probably turn this back on the participants and ask, What do you think it is? Is a capacitor an active element or a passive element? And of course, exactly the same question can apply to an inductor. Now, it is true that a capacitor can deliver power, but deliver energy, but the point is that you still consider it a passive element. It can only deliver the energy which is stored in it. Okay. So you start from a capacitor that is discharged. Now it cannot deliver any energy. It can absorb some energy and then give it back. Okay. In fact, that's a very useful mode of operation for a capacitor or an inductor. You can use that to store energy. Sometimes what happens is there are many cases in which circuit needs a lot of energy at some particular instance. So what you do is you arrange the circuit such that the capacitor is charged up and it stores energy, and during those instants of very high energy demand, it can give out energy. Okay, but we still consider it a passive element because you first have to supply energy to it and then take it out. Okay, I hope that is clear. Okay, now before we go further, let's be clear about a few things. Resistor V I, the power is I square R or V square by R, always dissipates power. Okay, and a capacitor and inductor, the energy is half CV square in a capacitor and half LI squared in an inductor. Okay, where I is the current at that instant. You see that the instantaneous power in a resistor will be the instantaneous voltage square divided by R or instantaneous current square times R. Now the instantaneous energy stored in a capacitor is the voltage at that instant square times half C. Similarly, the instantaneous energy stored in an inductor is the instantaneous current I times half L. Okay. And we also said that the voltage and current source can either absorb or deliver power. Okay. So the power is V times I, and you can also find out the energy. You can integrate the power over some time to see how much energy has been delivered by the voltage source or the current source over a given period. Okay. Now we know that the voltage V is measured in volts with the symbol positive V, and the current I is measured in amperes. The symbol is uppercase or capital A. Okay. Now the power, which is V times I, which is volts times ampere, is measured in, is denoted by units of watts, is measured in units of watts, denoted by W. Okay. So 1 watt equals 1 ampere times 1 volt. It also equals 1 ampere square times 1 ohm from this formula. This is just so that you get used to different ways of arriving at the units of watts, and it's also equal to 1 volt square divided by 1 ohm. Okay. And the energy E is measured in joules, denoted by J. Okay. Now we know that the energy is the time integral of power. So 1 joule equals 1 watt per second. Okay. So I think these are, mostly you are familiar with these things, but I am just refreshing your memory. Okay. And also we know that clearly the dimensions have to be consistent. So half C V square is the energy in a capacitor. So if you multiply farads with volt square, you will get units of joules. Similarly, half L IL square is the energy stored in an inductor, and if you multiply henries, the units for inductor, with ampere square, you get joules again. Okay. So whenever you do any calculations, please do it complete with units. Okay. There is not much point giving answers like the current is 1, right? It doesn't make any sense. It has some units, so it has current of 1 amp or 1 milliamp and so on. Okay. Similarly, the energy could be a joule or a picojoule or a nanojoule or whatever it is. Everything has to be specified with everything has to be specified with proper units. Now it appears that I made a mistake here. The power is the rate of change of energy. So 1 watt is 1 joule per 1 second, or 1 joule is 1 watt times 1 second. Okay. This means that if you deliver 1 joule of energy in 1 second, the average power is 1 watt. Alternatively, let's say you have a resistor and it is dissipating 1 watt, and if you wait for 1 second, it would have dissipated 1 joule of energy. Okay. Okay. Now again, we can do a couple of calculations just to get you used to these calculations. Let's say I have 1 milliamp current source. I think all of you know the prefixes. Milli is 10 to the minus 3 and micro is 10 to the minus 6, nano is 10 to the minus 9, and pico is 10 to the minus 12. These are the ones that we most frequently use. Okay. Going 1 milliamp and a 2 kilo ohm resistor connected across it. Okay. Now the question is, what is the power dissipated in the resistor? How much power is dissipated in the resistor? Please answer this. How much power is dissipated in the resistor? Okay, so now the current here, I is 1 milliamp, and the power dissipated is nothing but I square times R, which is 2 times 10 to the minus 3, this is 2 milliamp, right? Square times, sorry, 1 milliamp, not 2 milliamps, 1 milliamp times R, which is 2 kilo ohms, and kilo is nothing but, by the way, the other subscripts, so other prefixes more than unity are kilo of 10 to the 3 and mega of 10 to the 6, okay, and giga of 10 to the 9. So this will give you two times 10 to the 3 ohms. The entire result will come out to be 2 times 10 to the minus 3 watts, or 2 milliwatts. Okay. So the power dissipated is 2 milliwatts. Some of you said it is 2 watts, but please mind these units properly. Okay. Now, next is, let's say, I have 5-volt voltage source across a 10 nanofarad capacitor. Okay. How much energy is stored in the capacitor? How much is that? Please calculate. And similarly, you can also calculate if 1 milliamp is flowing through a 100 millihenry inductor, how much energy is stored in the inductor? Okay, I think by and large you have got this, it's just simple arithmetic. Here it is half and 10 nanofarads, which is 10 times 10 to the minus 9 farads, times V square, which is 5 square, which gives you, this is 25. 25 times 10 is 250, divided by 2 is 125. 125 times 10 to the minus 9 joules, or 125 nano joules. Okay. And in this case, the inductor energy is half Li square. The current is 1 milliampere, that is 10 to the minus 3 amperes, times, the inductor is 100 millihenries, which is 100 times 10 to the minus 3 henries, times 1 milliampere, which is 10 to the minus 3 squared. Okay. And this gives you 50 times 10 to the minus 9 joules, or 50 nano joules. Okay. So you should be able to do any of these calculations by yourselves from here onwards. Okay. Any elements or any simple circuit, you should be able to calculate the voltage and current in each element, and then calculate how much power or energy is dissipated or delivered in each element. Okay. Any questions about anything we have done so far? Okay. So what we have learned in this energy is the definition of power and energy in electrical elements. An inductor and capacitor store positive energy, and they can also be recovered. They don't really dissipate or lose any energy. So that's an important feature that distinguishes them from resistors, which constantly lose energy. Okay, they all continuously dissipate power as long as some current is flowing through them. And the voltage source and current source are the sources of energy, but it is possible for them to also dissipate energy or power. Okay. So if there are no further questions, what we'll do is we'll stop here and continue with the next lecture, where we'll discuss another element which is known as the mutual inductor, and then move on to circuit analysis. Okay? Any questions? Okay, then I'll see you in the next lecture.